Every finite element tutorial online shows you where to click in ANSYS. None of them show you what the software is actually doing. So in this series, we throw the black box away and build the whole thing ourselves in Python. Here's the simplest structural problem there is: a bar, fixed at one end, pulled at the other. How much does it stretch? If the bar is uniform, you learned the answer in your first mechanics class. PL/EA done. No computer needed. But real problems aren't uniform. What if the cross-section changes along the length? What if the material varies? What if the load is spread out unevenly? Now the tidy formula falls apart. There's no single equation for an arbitrary shape under arbitrary loading. This is exactly where most of engineering lies, and exactly where we need a method. The finite element method's whole idea is this: if you can't solve the hard shape, chop it into many small, simple pieces, elements each easy enough to handle exactly. Solve the pieces, stitch them together, and you've solved the whole. And it all starts with understanding a single element. So let's build one from scratch. Take a single bar element with two nodes, one at each end. Mechanically, it behaves exactly like a spring. Pull the ends apart and it resists, with a stiffness K equal to EA/L. Each node can move, call the displacements U1 and U2. And each node feels a force, F1 and F2. The element's whole job is to relate the two. Here's the key thought experiment. Push node 2 by 1 unit while holding node 1 still. The spring pushes back on node 2 with force K, and pulls on node 1 with force minus K, equal and opposite. Do that for every combination of pushing each node, and you fill in a 2 by 2 table, the element stiffness matrix. Forces on the left, displacements on the right, and this matrix in between. That little matrix is the entire physics of one element. Every finite element model, no matter how huge, is built from millions of these. Now the crucial step. Take two elements, A and B, joined at a shared middle node. 3 nodes total. Each element has its own 2 by 2 stiffness matrix. We want one big global matrix for all 3 nodes, so a 3 by 3. It starts empty. Now we drop each element's matrix into the rows and columns for its nodes. Element A connects nodes 1 and 2, so its 4 numbers go into the top left block, rows and columns 1 and 2. Element B connects nodes 2 and 3, so its numbers go into the bottom right block, rows and columns 2 and 3. But watch the center cell. The middle node belongs to both elements. So the center cell receives a contribution from A and from B. They don't replace each other, they add. 1 plus 1 becomes 2. And that's the whole secret of assembly. Wherever elements share a node, their stiffnesses overlap in some. Do this for 1,000,000 elements and you have the global system. It's just bookkeeping the computer does for you. Here's our assembled global matrix. But if we try to solve it right now, it fails. The math says the matrix is singular, it has no unique solution. The reason is physical. Nothing is holding the bar in place. Push it, and the whole thing just drifts off into space, infinitely many answers, because it was never anchored. So we add a boundary condition. Node 1 is fixed to the wall, its displacement is 0. That single constraint anchors everything. Because that displacement is known to be 0, we remove its row and its column from the system. What's left is the part we still need to find. That leaves a smaller, 2x2 system, and this one has a unique answer. The boundary condition turned an unsolvable problem into a solvable one. And here is everything we just built as real Python. There's no library doing the physics for us. The element matrix, the assembly loop, the boundary condition, the solve every line is ours, and you understand each one. The assembly loop is the overlap and add we animated. The two-line boundary step drops the fixed node. And then one call solves the system. That's the entire finite element method, start to finish. Run it on a 3-element bar, and out comes the displacement at every node, 0, 1, 2, 3. The tip moves 3 units. And the analytical formula, PL/EA, gives exactly 3. Our from-scratch solver nailed it, with code you could have written yourself. One more twist before we go. With a point load, our straight-line elements were exact. But under a spread-out load, the true solution is curved and straight elements can't bend. With one element, we approximate that curve with a single straight line. Close at the ends, but it misses the bulge in the middle. But add more elements, and the straight pieces hug the curve more and more tightly. And the error falls fast, 18%, then 4, then 1, then 0.25%. Each time we double the elements, the error drops by a factor of 4. That predictable shrinking of error is called convergence, and it's what makes the method trustworthy. Next episode, we'll see exactly why it works and meet the shape functions hiding inside every element. We built the machine today. Next, we understand its soul.